We will now have the last part of your Lesson 3, Stoichiometry in General Chemistry 1. So for this video, we will have two content: limiting and excess reagents and percent yield and theoretical yield. So for the objectives, we will explain the concept of limiting and excess reagents in a chemical reaction and calculate percent yield and theoretical yield of a reaction. So to start with, let's have the reason why we are discussing limiting and excess reagent. Chemist's goal is to produce maximum quantity of a useful compound from the starting materials. So to maximize the amount of products from the available reactants, chemists identify limiting reagents. So for economic reason and for mass production, the identification of limiting and excess reagents is important. So let's define the two. What is limiting reagent and what is excess reagent? Limiting reagent is the reactant in a reaction that is used up first completely. So in a chemical reaction, the limiting reagent is always consumed first before the other reactant. Excess reagent is the reactant present in greater amount than necessary. That's why it's called excess. It's more than necessary. Let's have an example. Consider the formation of nitrogen dioxide from nitrogen monoxide and oxygen. Suppose we have 8 moles of nitrogen monoxide and 7 moles of oxygen gas. So the corresponding chemical equation is we have 2 moles of nitrogen monoxide reacts with 1 mole of oxygen gas to produce 2 moles of nitrogen dioxide. So, as guide questions, to analyze and identify limiting and excess reagent and determine the amounts produced, the amount of the excess reagent left after the reaction, let's be guided by the following questions. So let us answer questions 1. How many moles of nitrogen dioxide are produced with each reactant? Number 2, which reactant gives us smaller moles of nitrogen dioxide, which is the product? 3, how many grams of nitrogen dioxide are produced with the given amount of limiting reagent? Because the amount of the desired product is dependent on the amount of the limiting reagent. 4, how many grams of oxygen gas will react with the amount of limiting reagent? So given the amount of the limiting reagent, after you have identified it, it will determine the amount of product or the amount of the other reactant needed for the complete reaction of the available limiting reagent. And number 5, how much will be left of the excess reagent? So let's answer the questions given the situation or the problem. How many moles of nitrogen dioxide are produced with each reactant? So again, the amounts of each reactant given is we have 8 moles of nitrogen monoxide and 7 moles of oxygen gas. We have the following mole ratios. 2 moles of nitrogen monoxide. Again, they are taken from the balanced chemical equation. So we have 2 moles of nitrogen monoxide plus 1 mole of oxygen gas equals or to produce 2 moles of nitrogen dioxide. So we have 2 mole ratios. 2 mole of nitrogen monoxide equals 2 moles of nitrogen dioxide. If we are after the product, the single product nitrogen monoxide dioxide. Another is 1 mole of oxygen gas to 2 moles of nitrogen gas. So as the first guide question indicates, we determine the number of moles of the product, nitrogen dioxide, to be formed with the available initial reactants, nitrogen monoxide and oxygen gas. So to do the calculation, we will be doing a mole-to-mole calculation. So in the previous video, in the last video, I discussed how the mole-to-mole calculation is done and how is mass-to-mass or gram-to-gram calculation is done. And between the two, it is easier because it is one step, the mole-to-mole calculation, which we will be doing here. So we start with the given mole of the one of the two reactants, nitrogen monoxide. So we have 8 moles of nitrogen monoxide is the given. Multiply that by the mole-mole ratio of that reactant to the mole of the product, nitrogen dioxide. So from the balance equation, we have 2 moles of nitrogen dioxide and 2 moles of nitrogen monoxide. So we have 2:2 or 2/2. We cancel the initial mole of nitrogen monoxide and the denominator of the conversion factor, we will have mole of nitrogen dioxide, which is our mole of product. So 8 times 2 divided by 2 will give you 8 moles of nitrogen dioxide. So given the other reactant 7 mole of oxygen gas, how many moles of the product will be formed from that available initial amount of oxygen? We have 7 moles of oxygen gas multiplied by the ratio this time of the mole of the product and the mole of the reactant oxygen. So from the balance equation, from the mole ratio, we have 2 moles of nitrogen dioxide over 1 mole of oxygen gas. You cancel again mole of oxygen to mole of oxygen, numerator, denominator. You will have moles of nitrogen dioxide. And 7 times 2 divided by 1 will give you 14 mole of nitrogen dioxide. Let's move on to question number 2. Which reagent gives the smaller moles of the product or nitrogen dioxide? It is moles of the 8 moles of nitrogen gave us the smaller number of moles of the product, 8 moles of nitrogen dioxide. That substance that gives the smallest amount of the desired product is the one that determines the limiting reagent. So in this case, between the two reactants, nitrogen dioxide and oxygen, nitrogen monoxide and oxygen, the one that gave us the smaller number of moles of the product is nitrogen monoxide. Therefore, nitrogen monoxide is our limiting reagent. So it means that in the reaction, it is used up first. It is completely used up first before the other reactant. So therefore, the other reactant in the reaction, oxygen gas, will be automatically our excess reagent. Let's go to question number 3. How many grams of nitrogen dioxide are produced with a given amount of limiting reagent? So again, the given amount of our limiting reagent is 8 moles of nitrogen monoxide. So in doing the calculation, because we will be needing here gram of nitrogen monoxide from the given amount of the limiting reagent. So this time we are given the mole of the limiting reagent, and we have to come up with the gram of the desired product, nitrogen dioxide. So we might be needing the following equivalent. So we have 1 mole of nitrogen monoxide equals 30 grams of nitrogen monoxide. 1 mole of nitrogen dioxide equals 46 grams. 1 mole of oxygen gas equals 32 grams. So to answer question number 3, let's calculate for the grams of nitrogen dioxide produced from the given amount of the limiting reagent. So again, the given amount of the limiting reagent is 8 moles of nitrogen monoxide. Multiply that by the relationship mole of nitrogen dioxide over mole of, or to mole of nitrogen monoxide from the balance equation. Again, they have 2 coefficients. So we have 2/2. You cancel mole of nitrogen monoxide and mole of nitrogen monoxide, numerator, denominator. Multiply again, use another conversion factor. So this is not a one-step conversion. This is not a mole to mole calculation. This time we are doing a mole to gram or mole to mass calculation. So in this case, we will be needing another conversion factor aside from the mole to mole ratio or equivalent relationship. So this time we will be needing the molar mass of our product, nitrogen dioxide, which from the previous slide, we have the equivalent 1 mole of nitrogen dioxide equals 46 grams of nitrogen dioxide. So using that as a conversion factor, we can now cancel mole of nitrogen dioxide numerator and mole of nitrogen dioxide denominator. We can now do the operation, solve 8 times 2 divide 2 times 46 gram, we will have the answer 368 gram of nitrogen dioxide. So to answer the question, 368 grams of nitrogen dioxide can be formed from 8 moles of nitrogen dioxide as the available amount of the limiting reagent. Let's go to question number 4. How many grams of oxygen will react with the given amount of limiting reagent? So as we said, what limits the amount of the product is the limiting reagent. In some problems, we might be asked to determine the amount of the excess reagent that is only necessary or that is required to react with the available limiting reagent. So this question is like that. So we are determining the amount of grams, or the amount of oxygen in grams that is needed to react with the available limiting reagent, which is 8 mole of nitrogen molecule. So to determine the gram of oxygen to react with 8 mole of nitrogen molecule, we will be needing to do another mole to gram calculation. So we start with the given amount of the limiting reagent. So again, because that is what limits the amount of product, and that is also our initial substance necessary in this calculation, because we need to determine the amount of oxygen needed to react with that amount of limiting reagent. So we start with the amount of the limiting reagent, which is 8 mole nitrogen monoxide. We multiply that by the mole to mole relationship, this time between mole of nitrogen monoxide and mole of oxygen gas. So from the balance equation, we see no coefficient with oxygen. So that means we had 1 mole of oxygen over 2 moles of nitrogen gas, nitrogen molecule, nitrogen oxide, monoxide, cancel, moles of nitrogen monoxide, multiply again because we need a gram of oxygen, not mole of oxygen. If the question goes, how many moles of oxygen is needed to react with the limiting reagent? So we stop with the first conversion factor, but we are asked to determine the grams of oxygen. So let's use another conversion factor. So this time we will consider the molar mass of oxygen gas, and the relationship 32 gram oxygen gas over 1 mole of oxygen we will be needing here. So we have a mole of oxygen cancel and mole of oxygen denominator cancel. So we will have gram of oxygen left as the final unit. So doing the operation, 8 divided by 2 times 32 gram, we will have 128 gram of oxygen gas. So to interpret, we have 128 grams of oxygen will react with 8 moles of available limiting reagent nitrogen monoxide. And for the last question, so given that we have identified the limiting reagent, we also have identified the amount of product produced from the available limiting reagent, we now compute for the amount of excess reagent in the reaction. So how much will be left of the excess reagent? So after identifying that oxygen is the excess reagent, we are now ready to compute for the excess amount of the excess reagent. So the initial amount of the excess reagent is 7 moles. 7 moles of oxygen is the initial amount. So to compute for the excess, we first determine the number of moles of oxygen needed to react with 8 moles. So again, the initial amount of the limiting reagent is 8 mole of nitrogen monoxide. You multiply that by, so you do a mole to mole calculation to get mole of oxygen from mole of nitrogen monoxide. So the initial amount of nitrogen monoxide, 8 moles of nitrogen monoxide, times the ratio 1 mole of oxygen gas over 2 moles of nitrogen monoxide, again, which the coefficients are taken, the moles are taken from the balance equation. We have 1 oxygen, 2 nitrogen monoxide coefficients. So you cancel mole of nitrogen monoxide, so you will have mole of oxygen. So that will give you 4 moles of oxygen. So to interpret, from 8 moles of nitrogen monoxide will react with, or will need for only 4 moles of oxygen gas to maximize the amount of nitrogen dioxide formed. So what then is the amount of the excess reagent left? So from the initial amount of 7 mole of oxygen gas, we subtract the calculated needed amount of oxygen, which is 4 moles. The difference is 3 moles of oxygen gas. That will now be the excess amount of the excess reagent, which is oxygen in our problem. Can we try this? The reaction iron 3 oxide plus 2 aluminum to produce aluminum oxide and 2 iron 2 moles of iron can generate temperatures approaching 3,000 degrees Celsius and is used in welding metals. In one process, 124 grams aluminum are reacted with 601 of ferric oxide. So you answer which of the two reactants is the limiting reagent. Calculate the mass of oxygen aluminum oxide formed, and how many grams or what amount of excess reagent in grams is left at the end of the reaction. So this is exactly similar to our example. So you just review those steps and answer this on your own. Moving on, let's now move on to the theoretical and percent yield. So let's first define these terms. Theoretical yield is the amount of product that will result if all, with the condition if all of the limiting reagent reacted. The actual yield is the amount of product that is actually obtained from the reaction. The percent yield is the proportion of the actual yield to the theoretical yield, and then we'll multiply by 1,000. So we have here the equation for the percent yield. So we have the ratio actual yield, theoretical yield. We have actual yield over or divided by the theoretical yield times 100%. Why is it that the theoretical yield is not always the same, or is not always the same as the actual yield? Why is it not necessary that the actual yield is smaller than the theoretical yield? Theoretical yield is the projected amount of product. That is the expected amount of product. But due to some factors, the actual yield is almost always different or smaller than the theoretical or calculated or projected yield. Two factors that may affect the amount of product formed from the amount of the reactants are temperature and pressure. So these affect the actual yield. Let's have this example. Titanium is a strong, lightweight, corrosion-resistant metal used in rockets and aircrafts. It is prepared by the reaction titanium 4 chloride plus 2 moles of magnesium equals or produces 1 mole of titanium and 2 moles of magnesium chloride. In a certain industrial operations, 3.54 times 7 raised to 7 gram of titanium 4 chloride are reacted with 1.13 times 10 raised to 7 gram of magnesium. 1. Calculate the theoretical yield of titanium in grams, and 2. Calculate the percent yield if 7.91 times 10 raised to 6 of titanium are actually obtained. So to answer the two questions, let's follow these strategies. Number 1, let's calculate the number of moles of titanium to be produced if all the available titanium chloride reacted. So in this case, we need to determine first the limiting reagent, because the limiting reagent is the one that controls or determines the amount of desired product formed. So let's calculate the amount of titanium to be produced. So what we are after here is to produce our desired product is titanium. So what amount of titanium can be produced from the given amounts of the reactants? So the two amounts of the reactants are 3.54 times 10 raised to 7 gram of titanium 4 chloride and 1.13 times 10 raised to 7 gram of magnesium. So to calculate for the amount of titanium produced from the first reactant, titanium 4 chloride, we have the initial 3.54 times 10 raised to 7 gram of titanium 4 chloride. Let's multiply that by the ratio 1 mole of titanium 4 chloride to its molar mass. The molar mass is 189.7 gram. So let's use the conversion factor from the mole-gram relationship of for titanium 4 chloride. 1 mole titanium 4 chloride over 189.7 gram of titanium 4 chloride, let's cancel gram of titanium 4 chloride, numerator, denominator, multiply again by the mole relationship between our product, desired product, and our initial product, titanium 4 chloride. So let's cancel again 1, 1. Mole of titanium chloride numerator and mole of titanium chloride denominator. The 1 titanium to 1 titanium 4 chloride ratio is taken from the balanced equation, which you can see on top. Cancel all the necessary units to be canceled, and then we'll have mole of titanium left as the final unit. So doing the operation, 3.54 times 10 raised to 7 divided by 1.89.7, we will have, because 1, 1, disregard, the answer is 1.87 times 10 raised to 5 mole of titanium. So that is the amount of titanium that can be produced from the available amount of titanium 4 chloride, 3.54 times 10 raised to 7 gram of titanium 4 chloride. Let's do number 2. After calculating the amount of titanium that can be made from one of the two reactants, let's now compute for the amount of titanium that can be made from the other available reactant, which is magnesium. The given amount of magnesium is 1.13 times 10 raised to 7 grams. So to compute for the moles of titanium that can be produced from that initial amount of magnesium, we do the calculation gram to mole of titanium. Stoichiometric calculation, that is gram to mole stoichiometric calculation. So we have 1.13 times 10 raised to 7 gram magnesium. Let's multiply that by the conversion factor, equivalent relationship mole to molar mass of magnesium. We have 1 mole of magnesium over 24.31 gram of magnesium is its atomic mass, which is also its molar mass. So we cancel gram of magnesium, numerator and denominator. Let's multiply again by another conversion factor, this time mole relationship between our product titanium and another reactant magnesium. So from the balance equation here, you will see the ratio is 1 mole titanium to 2 mole of magnesium. So we cancel mole of magnesium and another mole of magnesium to get the final answer, so we have 1.13 divided by 24.31 divided by 2 equals 2.32 times 10 raised to 5 mole of titanium. So now we have gotten the number of moles of titanium, our desired product, from the given initial amounts of the reactants titanium 4 chloride and magnesium. We now decide which of the two is the limiting reagent. So earlier, we had the amount of mole of titanium formed from the available titanium 4 chloride, and this one from the magnesium. So our limiting reagent, after doing the first two calculations, we have determined that titanium 4 chloride is the limiting reagent because it is the one that gave us the smaller number of moles of titanium, our desired product. So after identifying the limiting reagent, we now base the amount of titanium that can be produced from the available titanium 4 chloride, because again and again, the limiting reagent is the one that determines the amount of the desired product. So in our case, in our example, our limiting reagent is titanium 4 chloride. The initial amount is 1.87 times 10 raised to 5 moles of titanium. Let's review the question. Since titanium chloride is the limiting reagent, let's calculate the mass of titanium formed. We don't need to start from the given amount of titanium, because we have calculated in the first strategy 1, the amount of titanium that can be produced from the initial amount of titanium 4 chloride titanium for a reactant, and that is 1.87 times 10 raised to 5 moles of titanium. Let's now multiply that, so the step will be shorter this time because we have done the gram to mole calculation. So we are now doing just the mole to gram calculation from mole of titanium, the calculated mole of titanium, to the desired gram of titanium. So we have 1.87 times 10 raised to 5 mole of titanium times, we need the molar mass of titanium from the periodic table is 47.88 gram. Titanium, the atomic mass is equal its molar mass, or the same as molar mass. So we have 47.88 gram titanium over 1 mole titanium. Let's cancel mole of titanium. So we have 1.87 times 10 raised to 5 times 47.88 gram will give us 8.95 times 10 raised to 6 gram of titanium. So that is the amount of titanium that can be made from the available initial amount of titanium for chloride, because it is the limiting reagent. It determines this amount of titanium that can be formed from that amount. Let's now compute for the percent yield. So again, we are given in our problem the actual yield 7.91 times 10 raised to 6 titanium. So that actual yield, you will notice, is smaller than the theoretical yield, the one that we had calculated in strategy number 3. We had 8.99 times 10 raised to 6 titanium. So our theoretical and actual will be needed in calculating the percent yield. So again, the formula that I had given earlier, percent yield is equal to the actual yield divided by the theoretical yield times 100%. So substituting the given, we have the actual yield as 7.91 times 10 raised to 6 gram divided by the calculated theoretical yield, 8.95 times 10 raised to 6 gram, and then times 100. So we can simply cancel here the power of 10 because they are numerically the same. So we, using the calculator, pressing our calculator, we will have 7.91 exponent 6 divided by 8.95 exponent 6. We will have, and then multiply by 100, we will have 88.4%. So this is high. This is still higher, still close to 100. We have about 11.6 loss. No, because again, temperature, pressure may affect the actual yield. Can you try this one? In one process, 1.54 times 10 gram of vanadium 2 pentaoxide react with 1.96 times 10 raised to 3 gram of calcium. So 1, calculate the theoretical yield of vanadium. Vanadium is our desired product. Number 2, calculate the percent yield if 803 gram of vanadium are obtained. So doing the same steps as we did in the example, you can answer these on your own. So for generalization, let's answer the following questions. You go over your notes and answer the following questions. How do we write a balanced chemical equation to represent a chemical reaction? Number 2, how do we construct mole or mass ratio from stoichiometric calculations of the amount of reactant needed or amount of product in a chemical reaction? 3, how do we calculate percent and theoretical yields of a reaction? 4, what is the concept of limiting reagent and excess reagent, and how do we use them in calculating the percent yield of a reaction? So your answers to these questions will again wrap up our lesson 3, stoichiometry of your general chemistry 1. So this end our lesson 3. For the next videos, we will have lesson 4, which will tackle about gas loss. So that will be all. For other videos, you may press the subscribe and notification key. Thank you for watching and subscribing. See you again next time. Until next time. Bye.